Alright, so when measuring units like mass, length, and volume, it's imperative that we understand our metric and our SI unit conversions. As we highlighted earlier, we talked about meter being represented as a measurement for length. It can be also used for a measurement for volume when it's the cubic meter. So, moving on, we want to talk about significant figures and their role in chemistry and science altogether. Now, whenever you're trying to experimentally determine the degree of measurement, you always want to account for one degree of uncertainty. Now, in the image depicted, there's a graduated cylinder filled with a substance which likely could be water. And graduated cylinders are used to measure volumes, and it has the graduation lines. A zoomed in close-up picture shows you how this volume graduation lines can be measured, and you have to account for the measurement with at least one degree of uncertainty. Here you have 15, 16, 17, 18, and while you know the water level or meniscus curve falls somewhere between 17 and 18, you're not certain where exactly it falls between 17 and 18. Thus, your degree of uncertainty, which you incorporate by putting 17 point some number. For me, it might be 17.5. For you, it might be 17.6. In all cases, even if it's 17.0, you want to include that one degree of uncertainty for all your measurements, be it measuring a graduated cylinder or even using a gram scale. Now, I want to move on into applying significant figures both for a system of measurement and in understanding their principles when using them for math-related calculations. So, there are 4 rules that are dictated when it comes down to significance. Let's go ahead and establish that all non-zero digit numbers 1 through 9, are significant figures. That's not part of the rules, that's just an understanding. Now, ambiguity, or where the rules come into play, rest in their zero values. In Rule 1, if zeros are found between 2 non-zero digit numbers, those zeros are in fact significant. Rule 2 says that zeros found at the beginning of a number are not significant, but they only serve to locate the decimal point, so to speak. Rule 3 says that zeros found after the decimal point are significant only if there's a decimal point, and only if there's a decimal point, and only if there's a decimal point. If it seems like I'm emphasizing this decimal point, it's because I am. Rule 3, there has to be a decimal point. Otherwise, Rule 4 says that if there's no decimal point, the zeros to the right are so ambiguous that you don't know if it's significant or not, and therefore I would regard them as not significant. So, let's go ahead and look at some practice examples. Now, for each rule, I've gone ahead and created a problem. When we look at Rule 1, this one talks all about the sandwiched zeros. You have a zero found in between these 2 non-zero numbers, so that's going to be 3 figs. Likewise, there's a 3 here, there's a 9 on this side. This means that there's going to be a total of 4 in this one. Even though there's a decimal point, there are 2 non-zero digit numbers in this 10.09. This means that all of those zeros are significant, and therefore you have 4 significant figures for that number. And this Rule 1 only talks about the sandwiched zeros, or the zeros found between 2 non-zero digit numbers. Now, let's look at Rule 2. In Rule 2, we're focusing only on the behavior of the zeros, because obviously anything that's not a zero is going to be a significant number. In this case, these 2 zeros are not significant, therefore this only has 1 significant figure. The same can be said about this one. Even though there's obviously more zeros, this one also has 1 significant figure. Now, what's unique about this problem is it combines Rules 1 and Rule 2. In Rule 1, we understand that zeros found between 2 non-zero digit numbers are significant. It also says that zeros found to the left are not significant. So in this case, three numbers are significant. The 3, the 0, and the 9. These other two zeros are not significant. So let's move on down. Looking at rule number 3, we understand that the decimal point matters. If there's not a decimal point, you're looking at rule 4. But if there is a decimal point, all the zeros found to the right are significant. In this case, this has a 0 found to the right. 1, 2. Those zeros are significant. Therefore, you have 3 total significant figures here. When we look at this number, there's a decimal point there. And there's a non-zero digit number found on this left. So this 0, this 0, this 0, this 0, and even this 0 are all considered significant figures. So counting them up, 1, 2, 3, 4, 5, 6 is your number of significant figures. Now this last one's a doozy, especially if you haven't been exposed to scientific notation, but the rules are pretty much the same. You don't pay attention to this 10 raised to the exponent of 3. That's not what dictates the number of significant figures. What does dictate the number of significant figures are these numbers. And as the rules imply 1.2, and there's a 0 to the right, which means that there are going to be 3 significant figures there. So that's rule 3. But what if there is no decimal point? Well, enter rule 4. With rule 4, if there's no significant figure, then no zeros don't matter. So 1, 1, and 2. All because they feature zeros with no decimal points. Now lastly, let's look at one example that kind of combines some rules and look at how those rules can combine. So here we have a decimal point. This 0 does not matter. But the other ones do. This one is sandwiched between 2 non-zero digit numbers, and these 2 are found to the right of a number, and they have a decimal point. And those are significant only because of this decimal point. So in this case, this has 5 significant figures. So that's how those rules can play a role when identifying significant figures. But by extension, they can be used for so much more. And we'll look at that momentarily. Now, as I mentioned, some numbers are exact, some are vague, some are approximate. And when you talk about measurements, they can be ambiguous or exact. Now, when we talk about scientific notation, we look at this approximation or these values to solve for answers and determine whether something is used for a larger number or for a smaller number. In this example, they used the number 215. 215 can be broken down to equal 2.15 being equal to 100. Well, if you break down to 100, 100 is equal to 10 times 10. And 2 times 1.5 times parentheses 10 times 10 is still going to be equal to the same number. But if you replace those 10s with 10 squared, they mean the same thing as well. So when you're expressing something using scientific notation, you can do so by expressing them using 10 raised to a value of 2, and it makes a simpler expression of a much larger number. Now when the number is negative, or not negative, however, when the number is less than 1, meaning it falls in the decimal point range, then the exponent value that's being raised in that 10 place is negative. So if you see this negative number, the number is less than 1. If you see a positive number, the number is going to be greater than 1, or actually greater than 0. So restating that, positive exponent, decimal point is moved to the right. The number of places equal to the exponent. If it's negative, it's moved to the left. And you only use the significant numbers when you're solving using scientific notation. Now, the rules of rounding are a little bit different when it comes down to significant figures. Excuse me. When solving problems that deal with significant figures, there are a set of rules that are very important. There's going to be addition and subtraction, which is a set of rules. And then there's going to be multiplication and division when it comes down to a set of rules. So let's go ahead and look at a practical example once we discern between the difference of them. So rule 1 says that in carrying out multiplication or division, the answer cannot have more significant figures than the original numbers. That rule is not the same as rule 2, which says in carrying out addition or subtraction, the answer cannot have more digits after the decimal point than the original numbers. So to bring more depth to that, let's look at an example where we have to solve such a problem. First, we're going to focus on the rounding using multiplication and division. In the problems given, we have the numbers 309 and 2.0. 309 has 3 sig figs. The number 2.0 has 2 sigs. This means that even if we don't know what our answer is, the correct answer must have 2 sigs. Now, first we're going to solve for the raw answer, and then we're going to get the right answer. Now, the raw answer is not always the right answer. In this case, 309 times 2 is equal to 618. But that's not the right answer, because that has 3 sig figs. This has 3. And we need 2, because this has 2. It can be have no more sig figs than the numbers used to solve for the problem. This means that we must round this number to an appropriate number that will follow the regimen of having 2 significant figures. I'll give you a hint. You can't just drop the 8, because then it becomes 61. That number is nowhere near 618. What you have to do is round it to the nearest whole number that is close to that, but still occupies having 2 significant figures. The answer to this would be 620. Now, the reason that is the case is this 0 is not significant if it doesn't have a decimal point. So this has 2 sigs, and it checks out. It is not the same as 630, because 618 is closer to 620. 618 is not close to 610. It is close to 620. Excuse me. So, let's look at another such example. Here you have 100 being multiplied by 3.00. 100 has 1 sig fig. The number 3.00 has 3 sig figs. My answer must have 1 sig fig, no matter what I get. Now, because we know that 3 times 100 is going to be equal to the number 300. The number 300 has 1 significant figure. I do not need to add a decimal point, for if I did add a decimal point, that would make it have 3 significant figures. So it is dictated by the number of sig figs that are used to solve the problem. Now, let's look at just the rules of rounding when it applies to a number in general, because maybe the rounding part is a little bit of a challenge. So let's suppose we have this number here, 4329010, and we're asked how many number of significant figures it has. Well, I can tell you easily, this 0 is not significant, this 0 is, and all the non-zero digit numbers are significant. So therefore we have 6 significant figures. Now suppose one wants us to round it to have 5 significant figures. Can we do that? Well, I can tell you right now, if you try to, I don't know, write 43290 that's going to be wrong. That's not even the same number. That's not the same number. So what you're going to need to do is you're going to need to express it using scientific notation. For scientific notation, you take the number furthest to the left, apply a decimal point, 4.3 times 10, and I'm going to count from this place. 1, 2, 3, 4, 5. That gives me two significant figures if I wrote it like that. Now, why is that important? Well, I'll tell you. If we're trying to connect that so that it has five significant figures, we could apply the same principle by just playing 4.329, and we would have our five significant figures with that number there. That's why that's important. Now, with addition and subtraction, we want to look at the rules a little bit different. Recall that when you're carrying out addition or subtraction, the answer cannot have more digits after the decimal point than the original number. So let's go back and look at our example. Here we have 3 being added to 11.109. This means that these numbers are what we focus on. Because this has 2 here and this has 3, our answer must have no more than 2 numbers to the right of that decimal point. So I'll go ahead and put my decimal point right there. And I know that whatever my answer is supposed to have 2 there. So first we're going to solve for the raw answer, which might not be the right answer, and then we'll get the right answer, if that makes sense. So we have 14, 1, 0, and 9. Now that's the raw answer. It's not the right answer. And don't misunderstand that line is there as a separation bar, not as an actual distinct number. Now that's going to show our threshold for where our rounding should take place. If I'm looking for the correct answer expression of this, it should look like this: 14.1, and this is a 0, and I'm going to round up because this 9 can't be included, but it does influence that 0, and so that becomes 14.11. This is our answer. This is how you approach addition and subtraction, but not the same approach for multiplication and division. If this was multiplication and division, our answer would end up having 3 significant figures, but you notice ours has 4. Because significant figures has no basis for addition and subtraction, rounding rules. Alright, so revisiting our lecture. We're going to talk briefly about factor label method. Factor label method is a method of problem solving that allows us to convert between units of measurement. It is very effective when you have a conversion factor. And one such example, if you were trying to solve for something, you would need a conversion factor. And conversion factors are representative of the same numbers being equal to themselves. 12 inches is equal to 1 foot. 1 foot is equal to 12 inches. Things of that nature. And so that's kind of where we come from with that. So let's look at how we would solve a problem using factor label method. So if you're given a problem, you want to identify your given information. You want to think about what you need to solve it. Find the relationship that can be extracted and use that to solve the problem. So in an example where you have a child that is 21.5 inches long at birth, how long are they in centimeters? You would need to know what you're starting with, what you're solving for, and probably a conversion factor. And they use the same approach when they're solving that. So we're going to take a similar approach and try to solve this problem as well. So to solve it, I need to know that I have 21.5 inches, and I'm going to centimeters, and I need to know my conversion factor, which is 1 inch is equal to 2.54 centimeters. Now, because I know that, I can take 21.5 inches and write it out like this over 1. Identity function. Anything over 1 is equal to that number. Next, I want to solve for centimeters. So I need something that's going to allow me to get centimeters in my numerator position. And I'm going to put inches down here. And because I have inches up here, I have inches down there. That's kind of how they're going to, because they're going to cancel out. I'm going to take this conversion factor. This is my conversion factor down here. And I know that 2.54 centimeters is equal to 1 inch. And when I solve, I'm going to multiply everything on the top and divide by whatever numbers are found on the bottom. So 21.5 times 2.54 centimeters should get me my answer in centimeters. And that's how you apply factor conversion method. So, last little tidbits and then we should be done. Energy represents the capacity to do work. We need to understand that temperature is a measure of the amount of heat energy, and there are degree of measurements that we're familiar with or may have heard of, such as Fahrenheit and Celsius, and there are new ones that we need to know, which is Kelvin. For all intended purposes, you definitely want to know how to convert between Kelvin and Celsius because they're very similar. They move by 1 degree or 1 in general. For 1 Kelvin of change, there's 1 degree of Celsius. For Fahrenheit, it's a little bit different, but our focus should primarily be on the conversions between Kelvin and Celsius. Kelvin is equal to degrees Celsius, and to get that, you add whatever number you have in degrees Celsius to 273.15 or 273, and that'll get you Kelvin. And if you have Kelvin and try to seek out Celsius, you can take the Kelvin temperature and subtract 273. And there are a lot of things that are temperature sensitive out there. We won't spend a great deal talking about those, but density represents a derived unit of the SI units. It's a relationship between mass and volume, and it can be used to solve for the identity of a compound, provided that the temperature conditions are static or the same. Because density can actually be influenced indirectly by temperature, if you will. Temperature affects volume, which inherently will affect the density. So water is generally the staple, and it has a density of 1 gram per milliliter at 25 degrees Celsius.